minus 3 points again, but now the Galois action on P1 minus 3 points. Only I have to, okay, now basically everything I will say is all too well known to experts. Because, well, these are things which have to be said by someone, unless we assume that there are only experts in the room. So let me first recall the short exact sequence for pi1s, because that's, I would say, unavoidable. So it says GA1. So SGA1, just, I'm not recalling SGA1, just a very tiny piece, which is the short exact sequence for fundamental groups. So let's say you take X over K, a scheme, which is nice enough, which means either it's regular, or it can be only normal, that's okay. K is a field, K anything, K a field. Now, pi1 of X, okay, it's really streamlining, because it has to be said. And where, so it's the limit, inverse limit, of the isomorphisms of Y over X, where Y is Galois finite. Well, finite, you don't have to say it because it's contained in étale. Okay. Now étale is unramified and flat, but flat doesn't really enter because we say K field to make it simpler. And then we write pi1, the geometric pi1 of X is pi1. Well, I didn't define, yeah, no, I did. Tensor K bar. So K bar is a separable, it's actually a K bar A. So we choose a separable closure. Closure of K. And then you check that pi1 of spec K is nothing, well, this is important to remember. Okay, actually you need base points. So let me forget about base points, because we'll never need base points. Well, we will, but not now. So here you would need base point, and choosing a base point, a geometric base point, is exactly like choosing a separable closure. But it's nice to remember that in this language, this is a notation. This is just a notation, just to make it simple, to make it shorter. And so you have this, and now you have the basic short exact sequence, which is this. So this is the basic short exact sequence. This sequence is exact. So this is in SGA1. So it says that in some sense, the pi1 of X, which is given by the étale covers of X, breaks into a arithmetic part and so-called geometric parts in the sense that we've eliminated arithmetic by taking a closure. Okay, now maybe I'll say why out of this you can derive the three main branches I alluded to: an abelian geometry, section conjecture, and GT theory. So you have this sequence for any X. So this implies that this implies completely formally, like for any exact sequence, that there's a map from GK to the outer automorphism group of pi1 geom of X. So this is a completely, well, sort of quote unquote formal. I mean, any short exact sequence will give you an outer automorphism. Outer automorphism means automorphism modulo inner automorphism. So that's, here I can forget about base points, precisely because it's outer. And any exact sequence will, a short exact sequence will give you an outer action of the quotient on the kernel. That's very easy. Okay, given this, what do? First, you can, so I'll go to, of course, Grothendieck-Teichmüller theory, but what is an abelian theory? What do I want to say? First I'll say that, what do I want to say? I want to say the three thing, yeah. I want to tell you just a little bit, no, just state what is now, has now become known as IOM for Hihara, Oda, Matsumoto, which will be basically the subject of the talk of Florian Popp. And this is very, in some sense, it's a counterpoint to Grothendieck-Teichmüller theory. So what does it say? It says if you have this, then suppose you have a collection of, say, a category of, so C is a category of smooth schemes. No, smooth, I mean, regular. Well, regular or normal, doesn't matter. Regular schemes or varieties, regular, normal, varieties over K. So when I say a category, it simply means that I have objects and I have the morphism, and the morphism are simply the morphism between the schemes which are defined over K. So they are K morphisms. So everything is over K, both the objects and the morphism. Then I have, then for any X, I can define pi1 geom, and I can consider pi1 geom as a functor. So it's a functor from where to where? From C to profinite groups modulo inners. So it's a functor from the category C to the profinite groups modulo inner automorphisms. Then GK is a functor, then GK, then you write the same thing. It's just a little more fancy, but it's exactly the same thing. So what the automorphism group of, or maybe here I can write all. It's the automorphism group of that functor, which means the invertible, sorry, profinite groups, mod inner automorphisms. Maybe I should have defined a profinite groups. The morphisms are what here? Oh, and oh yeah, and the morphisms are between this and that. Yeah, are modulo inners. Yeah, like pi1 geom. Oh yeah, of course. So you have this, and you will see that, okay, so the problem is under, yeah, exactly. So question, when is this an isomorphism? So this is a very natural question. So the Galois group acts of K acts on well in an outer way on the pi1 geom. And when is this an isomorphism? So we'll see that it's very easy. It's very easily. I have no name. How do I call it? Oh, it's the action of the Galois action. Let's say call it the Galois action. Actually, with Leila, we produced a book. We edited a book which was called Geometric Galois Action because it's GGA, and Grothendieck produced EGA, and there is FGA. FGA is fundamental, so we produced GGA. So a long, long time ago. So this is the Galois action. So where is the Galois action? So we'll see that even if you have x equals just as soon as the category contains p1 minus 3 points, it's injective. That's Belyi theorem. Oops. It's a consequence of Belyi theorem. But the problem is, when is it surjective? That is, when is it that there are no other automorphisms than the Galois group? And the answer is, the answer it has been proved, and you need actually much less. So let's say on faire talk by Florian talk. Okay, so this is part of, say, birational Abelian geometry. In fact, Abelian geometry in general asks the question: what are the x's, so that this contains all the knowledge about x, which means it's reconstruct the homotopy type of x in particular. So I'm not going about further. So the section conjecture is as follows. Maybe I should say here that any rational points here, any k points of x provides a section of let me call it star of this fundamental of this. Why? If you're simply a little abstract, what is a k point is just something like this. No. It's actually it's actually very often the case. You actually need very few. It's surprisingly few varieties, and actually much less than pi1. Just a tiny quotient of pi1 geom, and it will already be. This is the striking thing, and it will be injected. I'll show you. It's injective by Belyi theorem. Belyi theorem will tell you that it's injective. It's injective if the category contains p1 minus 3 points. So the section conjecture says, so any rational points will provide a section, because if you take pi1 of this, then you get something from gk to pi1 of x, which is a section. By the way, this, if you are a bit of an algebraized topologist. Sorry. In case k, in case k is a number field, say. Yeah. No, they're not proving it for all k's. I mean, it's not true for all k's. So I write it as a question. Yeah, of course, Belyi proves it for p1 minus 3 point over q. Yeah. So maybe I shouldn't write it. I mean, just You think of this as a fibration where this is the fiber, and then you have a long exact sequence, and this short exact sequence, say pi2 of spec k equals 0, which is very believable. And if you have the good framework, it's just true. Okay, but the section conjecture say that if let k be a number field, which is a finite extension of Q, X closed. Okay, so it's not P1 minus 3 point, a closed hyperbolic surface. Curve, I mean. Then over K. Okay, then all sections of star are given by, come from rational points. Come from K points of X. So there are no other sections up to, I think automorphisms of P1 geom. There are no, all the sections are given by points. That was also a question, I think I'm not sure it's in the Esquisse, but that was a question Grothendieck was asking. It's again about pi1. It's very, very specialized. I mean, X is a curve, it's a hyperbolic curve, and it's a closed, because if it's not closed, you have all these tangential base points and so on. It's another story. I mean, no, it's not another story, but it's a little more, it's more cumbersome. So this is a conjecture, but there are, I mean, there's some things have been proved, not over number fields, I think over p-adic fields more. Okay, now let's return to our good old P1 minus 3 points. Let's return to P1 minus 3 points. So this gives you an idea about abelian geometry, section conjecture, and this. And we're all in the framework of curves. Okay, so everything is dimension 1 here. Okay, maybe I erase this. And okay, so let's go back to P1 minus 3 points. So if you specialize this to P1 minus 3 point, you simply have 1. Okay, now, well, so I'll write X equals P1 over Q minus 0, 1, infinity. So I rewrite this sequence, so 1, P1 beyond X, P1 of X, GQ, 1. So now what is this? This is a surprisingly long story too, but although you can also consider it as somewhat trivial, but no, it's not trivial, but it's the answer is that this is the profinite completion of the free group on 2 generators. So F2 equals the free group on 2 generators. I have to write at least once what is the profinite completion of a group. Maybe all of you know it, but if I don't write it down once, it's bad. So reminder, if G is G a discrete group, maybe somebody will write the definition of a pro-unipotent completion at some point, but here G hat is the inverse limit of G over N, where N is N as finite index in G. So I write profinite. Profinite means finite index. Actually, if G discrete group, all the groups which come from geometry are finitely generated. It's very nice to be finitely generated, because when you're finitely generated, then not only the normal subgroup, but in fact, all the invariant subgroups, the so-called characteristic subgroups, are cofinal. So here I can write Galois, I can write normal subgroup, which are cofinite. I can write invariant subgroup if I want. So here I'll write discrete finitely generated, because all the groups coming from geometry are finitely generated. Coming from geometry simply mean that they're pi1 of something, of a variety, a scheme, a stack, or whatever. Okay, so this is the, okay, but now why is this true? Then what, you have to apply some sort of GAGA type theorem, SGA1 chapter 12. So you have to have something which tells you that pi1 of P1 minus, pi1 of the plane minus 0 and 1 is, of course, F2. Okay, it's the free group on two generators. So to say that when you go to Q bar, you just have the profinite completion, you have to descend from C to Q bar, and also to prove a GAGA result for Q bar. And also, since it's P1 minus 3 points, it's not closed because, well, it's not closed because they're cusps. And so it's a bit annoying, in fact. If literally speaking, the famous problème des trois points, which was in SGA1, was to compute P1, to compute this without using any GAGA result, without using anything, in a purely algebraic way. So strictly speaking, this is not even done now. So that was 1959. Even here, the GAGA results, you have to have descents between algebraically closed group, and then you have a GAGA type result for this. Not for this, because for this doesn't mean anything. So okay, but the result is true, and it's not easy to find a good reference which tells you that this is true. To go to the very core of them, I mean, down to details, but this is true. So you have GQ acting on this. So I don't have time to do everything. Okay, we'll have to take a tangential base point at some point. It's very easy. Tangential base points, I don't know why people have done so much about them, because it's a very easy thing, in fact. But you have, say, if I choose a base point, which will actually be a tangential base point, then you have a map like this, and it turns out, right, no, it's not, does not turn out, but this is spaceful, and this is spaceful because of Belyi. The result. Okay. So now, and this is at the very beginning what I said. That's what the thing that really Grothendieck found striking, that you have a faithful action of the Galois group of Q on F2 hat, and it's faithful. Now I'll try to, well, I will show you how to make it more concrete. So how do you write P1 minus 3 points? How do you write this F2 hat? Then you do this. It's a famous, you have 0, you have 1. I just want to see what colors and then what kind of, yeah, let me write it this way. So here you have 0, 1. Here you have what is called 1, 0. I'll explain. Here I have this, which I call X. Here I have, so it's really a matter of, here it's more a matter of, almost a matter of notations. No, sorry, Yeah, this is what I meant. Yeah, this is what I meant. Okay. And I'll write this like P, this like X. Okay, so you have the point 0, the point 1. This is a tangential base point, which is usually called 0, 1. I will explain or not explain. I wanted to explain, but if you had said that to Riemann, he said, yes, I call it a cut. And a cut like this. But now, okay, you have to talk about Puiseux series and sorts of things like that. Maybe I'll have time, maybe not. So you have one, so our preferred base point is 0, 1. P1 of P1 Q bar of minus 0, 1, infinity with base point 0, 1. This is still F2 hat. It's topologically generated by X and Y, which are two loops. One is this one, and the other one is, since you have to start from the base point, you take P, this, and this. So if I write the automorphisms, theta goes to 1 minus t, omega goes to t over, I think, 1 over 1 minus t. These are the two automorphisms of the space. So the group generated by theta and omega is a group. It's a substitution group on 0, 1, infinity of three points. So here you have t goes to 0 goes to 1, 1 goes to infinity, infinity goes to 0. So you have this recycle. Here you have 0 goes to 1, 1 goes to 0. And then you have, so you have P. P is so what Deligne called the droit chemin. P equals droit chemin. So you have to hear that droit chemin, the straight path from 0, 1 to 1, 0. But in French, the droit chemin has a very strong moral overtone. Droit chemin is the thing you should do. So it has a strong moral overtone, but it's only the straight path. It's the straight path in life, but it's also the straight path from 0, 1 to 1, 0. So it's straight from 0, 1 to 1, 0. And in some sense, P will conceal the whole secret of, I would even say, of Grothendieck-Teichmüller theory in a way. So I have X, Y is nothing but P first, then followed by theta of X, followed by P minus 1. Simply you do this, and you do this. Okay? Now, I have to, now you want to compute this action. So you see that theta and omega are defined over Q, which is only a highbrow way of saying that it's obvious because they contain only rational numbers and very simple ones for that matter. So if I'll tell you exactly what the action is first, next, but if I want to write, what I want to compute is, I take a sigma in GQ, and I want to compute sigma X and sigma Y. But sigma X, I'll show you, sigma Y is nothing but sigma of P minus 1, theta of sigma of X, sigma P. What I said about being defined over Q means that sigma can go through theta, because theta is 1 minus t. It's defined over Q is, again, a grand way of saying that you can do this. So what you really want to compute is sigma of X and sigma of P. Sigma X and sigma P, okay? Now, if you go to, I'm not going to do that. I'm not going to do what I'm just going to say, which is, if you go to that, for instance, but there are other references to that volume we wrote a quarter of a century ago. You will see that this has to do with commutativity. Oh God, too many letters. Commutativity. And this has to do with associativity. So it has to do with, X has to do with commutativity, P has to do with associativity. Maybe I'll give you just a glimpse of why P has to do with associativity. Write it this way and say, and take P1 minus 4 points. You have 0, 1, and here you have lambda. And here you have infinity somewhere. And lambda goes from 0 to 1, okay? Now there are many, many ways of, and they're not analogies. There are many ways, given what I said in the first lecture, of drawing this in a completely different way. One way is to say that, this. It's almost the drawing I made at the very end. One way is to say this. And we have good reason to do that. I mean, it's not analogies, it's just identity. So you have, on the one hand, you have 0 and lambda and 1 infinity when lambda is here. And when lambda is here, it's the exact, it's a completely different picture, which you can do like this, for instance. Which is lambda is with infinity and 0 is with 1. So it's changing this into this, for instance. I can't really explain. It's also changing this to this. And this is associativity, properly speaking. This is also many other things. But the only thing I would like you to remember is that P has a lot to do with associativity, X has a lot to do with commutativity, and that explains why, sort of explain, why P is the most important thing here, by far. And that let's say the very mystery of Grothendieck-Teichmüller theory is in some sense contained in P and the modularized tax of curves and many, many other things. So here that concentrates a lot of the mystery. So let's do this. Let's write it more precisely. By the way, in another century, we wrote, Hihara wrote a paper in a book maybe in that book, in GGA2. Yeah, we co-edited at the end of another century. And I wrote an appendix with Michel M. Salem, where everything I'm saying is, and much more is written down. So again, you don't have to worry. And this is on my webpage, so you don't have to worry about taking notes or anything. So the answer is, here you have a clear answer. Sigma x is nothing but x to the sigma, to the chi sigma, where chi sigma is a cyclotomic character from GQ to Z hat cross. The chi sigma, so remember Kronecker-Weber. Kronecker-Weber says that GQ, that adding the roots of unity, all the roots of unity, will give you the maximal abelian quotient of GQ, where Q ab is Q with all Q, where you adjunct all the roots of unity. Okay, so chi of sigma is the thing which the character of this. I mean, it's a character, so it factorizes through the abelian quotient. So the answer is this. So you see, commutativity in terms of GAGA action is just summarized by the cyclotomic character. So that expresses deformation of commutativity. So in some sense, quote unquote, it's not fun. You're done. So what about the other one? The other one, you should compute sigma y, but sigma y is this, so you compute sigma p. So sigma p, you have just no idea what it is. So since you have no idea what it is, yeah. Oh, sorry. What do I want to say? Yeah. So, well, no, it's still true that you can, it's a quotient, but yeah. Yeah, it's the abelian quotient. No. It's a GAGA group of, no, it's not GQ ab. Yeah, it's a quotient. How do you write it? GQ ab. Yeah. Ab is upstairs. Yeah. And so, and GQ ab upstairs. Yeah, that's just Q ab. Yeah, that's why I wrote Q ab. Yeah. No, yeah. So sigma p. Do I write p of sigma or sigma p? Sorry. Yes. The invertible elements of the hat. Say it again, sorry. Oh, what does it mean? Yeah. I'm about to write something which is even worse. So just a sec. I'm about to, not even worse, but no, one is a quotient, is a kernel, yeah. Sigma p. Yeah. So this is sort of an empty statement. It's not empty, it's the definition of this. So here you have to, I'll skip a few things that, okay, sigma p, you know that sigma p will go from, and f will go from 0, 1. Sigma p will actually go from the same, will join the same base points. So f sigma of xy is just an element of pi 1 of this, so it's an element of f2 hat. And here you have to say a few things because I write it. It's a bit bold to write it f sigma of x and y, because x and y generate topologically generate f2 hat. So you have to say that this is like a change of variable or like a change of a way of writing a change of variable. Actually, if I have a map from a free group to a profinite group, I can write the elements of the element of the image in terms of the image of and if it's surjective, then I can write the element of G hat as elements in terms of the element of Fn. In terms, but of course, F sigma is profinite. Let's stay here because, okay, then you have to go into the fact that the profinite completion is a universal completion and a few things, but But okay, everybody sort of understands what that means. That F sigma is just an element of F2 hat, and I can write it as F sigma of xy. It's just a way of writing. So once you've written this, which again is just a definition, nothing more, what do you discover? Well, first you discover that F sigma is P minus 1 sigma P. And this is, I'll say it very quickly. This is a non-abelian cocycle. And if I map F sigma to the non-abelian cohomology of GQ with coefficient is in the groupoid, in the pi1 groupoid, then this is essentially the Kim-Chaboty map. This is the Kim-Chaboty, what they actually study, except not in the profinite situation. Because if I take another P, actually it does not, this cohomology class does not depend on P. It depends only on the fact that you have a path from 0, 1 to 1, 0. Because otherwise you get if you change P, you will get an equivalent cocycle. So this was just a remark. So one way of saying, not saying, but let's say of taming F sigma is precisely this. And then you have a beautiful theory. Another way is to say a sigma with the proper, yeah. In order to justify this, how do you map this to the outer automorphism group? You simply consider this as an element of this, and this you take you consider it as an outer automorphism. So what you do is you simply they say the long and the short is that if I have a path, this is nothing but sigma gamma at sigma minus 1, where I have to define, or maybe the other way around, I don't know. I mean, you choose. So no, yeah, this. But I would have to explain what I will, maybe I won't. It's depending on time, but it's certainly explained in the paper what it means to say that when sigma acts on a path, it's what it does. It's simply you have a sigma which is here. You have a path which is here. You map it to here, and you let sigma act like sigma gamma sigma minus 1, and this is well defined if you don't choose the base point. So this is it. So if you write it this way with the proper conventions, you find that F sigma is nothing but the commutator of sigma and P, which is, it means that the Galois action and the path groupoid do not commute, but the commutator is what you're after. Okay, so it's one way. I like this way of saying, in a way, because you see that what you're trying to do is to see how the Galois action and the groupoid commute, and they don't. And this is the failure of commutation you're trying to compute. Okay, now in this hour I haven't done very much, in the sense that there's a lot more to be said. And how do you, maybe what I can do is try to explain how you compute even this. Why is this true? Why is this true, for instance? Or how do you compute F sigma? So what you do is, you do it very literally. You do literally what I said. about the Galois action. So you take a function on your, this is very instructive. No, it's an element of the groupoid with 6 base points, which are, you know, I take P. No, it's yeah. You have to be careful. It's a commutation of the Galois group with something which is not exactly in a group. Yeah, it's actually what we're working with, the groupoid of X with 6 base points, 0, 1, 1, 0, and the same at 1, and the same at infinity. So you have 6 tangential base points. Now, what does this mean? What does this all mean in a very, very concrete way? Once you have, it's a very instructive thing to disentangle everything I said from this. So you take this, you take this, you take x equals p1 minus 3 points, you take, yeah, this, and you try to see what it means. What does it really mean? It means that, what does it mean? What it really means, let's see, sorry, I tried to see, if I had a more general, I want to do it in a general way, because let's say, let's put it this way. I take a function on y. Now it looks like this. I take an analytic function of y on y. Why does it look like this? Because what does this mean? I take the formal expansion of this is the formal expansion of a function on y at a certain point on over the base point 0, 1. And this is the E is the ramification index at that point. And to say that I take a tangential base point is that I can expand my function in Puiseux series, non-Laurent series. Okay, and that's exactly what I have. I mean, and now if I have the germ of the function at 0, 1, then that determines the function because it's an analytic function. So actually what is all that thing about tangential base points and so on amounts to is to say that I'm working with functions which have a Puiseux expansion at a certain point over over 0, 1. And to choose a base point is to choose a coherent sequence of base points on all the y's, which means choosing a base point on the formal universal cover of X. So I take this function and I do exactly what I said, which is simply you map F, you map this to, remember this recipe. This is the recipe. So, so I map this to by sigma minus 1 to sum of sigma minus 1 of an t to the n over e. Then comes the mysterious part, which is analytic continuation. What is mysterious is always simply analytic continuation. So you analytically continue this to 1. Well, of course, I cannot. This is the non-explicit part. If I take any gamma, a gamma for that matter is anything in P1 in the groupoid base at the 6 base points. So it's not X for the time being. It's just anything. E is the ramification index of y at the point where I'm expanding the function. But I've chosen a base point over 0, 1. Okay, over 0, 1, x, I have this. I have 0, 1 downstairs on x, and on y, I have various ramifications, and I've chosen a base point here, and here E would be 3, for instance. So I do this, then this I don't know. This I just don't know what it is. So I write Bn, and I expand again. It may not be the same E, but let's pretend it's the same E. And now I do sigma, n, sigma Bn, 1 minus t to the n over E. And that's it. And that's the result. Okay, but that doesn't tell me much if gamma is anything. Now, if gamma equals x, it's much simpler. What does it say if gamma equals x? If gamma equals x, so let's specialize to gamma equals x. Then we're going to 0, 1, 2, 0, 1. So then x is, this time is in the pi 1 of x with base point 0, 1. So you take this function, you map to, again, I mean, this. But this time, you want to, you do x, it's not any path. So then you get sigma of n, zeta of, you get, yeah. So zeta is an E root of unity. This is the result of applying x to this. So it simply says that if I go around 0, I get this factor, zeta and E root. I mean, the E root of unity is zeta equal, well, actually 2I pi over E. And then I do, sorry, the sigma 1 stays. No, it doesn't stay. What do I want to say? Yeah, I know it says. And then I do sigma, and then I get an zeta to the n chi of sigma t to the n over E. And the Galois action is simply mapping this to this. And here you see that if I do x alone, I'll get zeta to the n, not zeta to the, I'll get this. I don't get chi of sigma. And the upshot is, so if I do the same thing with x without the sigmas, instead of chi of sigma x, I get zeta to the n. And this is the thing which tells me that the computation, which tells me that sigma x is x to the chi of sigma. In essence, it's quite simple. Either you go around x, you go around 0, and nothing, and via x, and nothing happens. But if you go around x, and first you do sigma, then you go around x, then you do sigma, then you pick a factor, which is this. That's it. So this was to illustrate, maybe clumsily, that you get this formula. So this is done a little more neatly there. So you get this. Now, F sigma will be much talked about, because this is where you encounter, F sigma, let's say the pro-unipotent version of F sigma will be much talked about. This is where you encounter the Drinfeld associator, the multiple zeta values, everything, okay? F sigma, I'll try to talk about also F sigma in the, or the thing which, let's say the Galois, the Grothendieck-Teichmüller group is built out of chi of sigma and F of sigma. Now you erase sigma, chi of sigma, you call it lambda, F of sigma, you call it F, and you get the Grothendieck-Teichmüller group with many, many stories to come. These are the two parameters. One parameter is just, unfortunately, you know, Russian people are, they think the Greek alphabet is a weird thing. So instead of choosing chi, which would have been obvious, Grünfeld chose lambda for some reason. So it would have been more, let's say, more natural to choose chi rather than lambda. But okay, it chose lambda. So you have lambda and you have F, which is the substitute for F, in the Galois case is F sigma. So these are the parameters of the Grothendieck-Teichmüller group. Again, the lambda or the chi of sigma is relatively simple. It's simple. It comes from commutativity in a different context. The whole thing is about deforming associativity, or the droit chemin, P, or all the kind of pictures I had, or braids, or everything. Everything you can say in terms of F. And this will be basically the subject of the workshop in a way. Thank you. What is a groupoid? It's just a mild generalization of a group. That is, you have the path. Oh, well, the groupoid, again, you take you have 0, 1, I have to put infinity somewhere, and you just have the 6 tangential base points, which are these ones. So I have six tangential base points. Here I write 0, infinity 1, infinity 0. I mean, this is the main, this is the object, yeah. This is simply because there is no preferred base point on P1 minus 3 points. So again, if you had told this to Riemann, he would have said yes, of course, because tangential base points are nothing but saying that if I have this and I remove that point, then this tiny neighborhood is certainly not simply connected. How do I make it simply connected? By adding a cut here. How do I express a cut algebraically? By taking this. How do I say algebraically? By taking Puiseux series instead of Laurent series. That's it. Okay, then you can write it in a fancy way. Sorry? Yeah, a path between a base point and a point in itself is the pi1, and then a groupoid is a path between two base points. Oh yeah, of course, these base points are fixed by the action of GQ. That's why I wrote this. That's why I could write that sigma p is P. That sigma p goes between the same base points. So I write it as a definition. I write F sigma like this, because I can first do this and then do this. If you're fancy, I don't know, something is a bitorsor about something.
Any more questions?
Yeah. All of this, that's what I said. You have to, I mean, there are also GAGA results between two algebraically closed fields, for instance, between C and Q bar typically, which we use because just to say that is F2 hat, for instance. Because normally you go from Q bar to Q and C to Q bar. Sorry, normally you take in GAGA type results, you start from a topological thing or from something over C, and if it's over Q bar, you have to say it's the same thing. So it's between algebraically closed fields. But nothing happens for Galois in between algebraically closed fields.
Any more questions? If not, let's thank the speaker again, and we'll meet at 3 p.m. for the talk by Professor Nakamura.
So
3 p.m.
3 p.m. And again, maybe I say that if people want to give talks, so-called young researchers, or maybe of any age, then they should come and see us, and we can